Hi, my name is Bryce Summers, and today I'm going to talk about how to compute the determinant of any 3 by 3 matrix. You can use these same techniques to compute the determinant of any square matrix, 4 by 4, a million by a million, or a 2 by 2. So let's get on with it. If you'd like to read the different helpful hints about properties of the determinant, you're always free to pause the video whenever you'd like. But for those of you who have not yet paused it, I'm going to go on and talk about computing the determinant using the Summers Camp program. So we have an algebraically arbitrary matrix here that represents any 3 by 3 matrix possible, because we've called the different elements A, B, C, D, E, F, G, H, and I. So we're going to compute the determinant of this expression. The first thing we do, of course, is we go into determinant mode. To go into determinant mode, we click on the Det button, which stands for determinant, and we click on it to toggle determinant mode. Since we're in determinant mode, this enables useful scalars to show up to give us information that will help us when we're computing. We're going to compute the determinant using a process very similar to Gaussian elimination. We're going to be row reducing the matrix while remembering different numbers about based on the different determinant based on the definition of the determinant. So let's begin. First we're gonna use the same strategy we do like we always do in row reducing, where we're going to try to create zeros. We're going to try to create a zero here, here, and here. Once all of these are zero by rule number 4, the determinant of this matrix will be equal to the product of each element on the diagonal. But throughout this process, we'll actually be changing the determinant. That's why we'll be using these scalar boxes to keep track of the scalar we need to multiply the final result by to compute the result of the original matrix. So let's create this first zero. We'd like to create a zero in this row. So row 1 is the one we'd like to mutate, and we always click on the row we'd like to mutate first. So we click on row number 1. Now what would we like to do? Well, we'd like to subtract some multiple of row 0 from row 1 such that this D disappears. So we're going to subtract D divided by A times row 0. See? So by dividing it by multiplying it, dividing it by D, but by dividing row 0 by A will become 1, and by multiplying by D, the 1 will become D, and by subtracting D from D, we will create 0. So now we're going to evaluate this. See? Now row 1 has gone to row 1 minus. I'm going to use some formatting. /frac creates a fraction. Let's see. What did we do? D A times, or let's see if that works. Nope, that doesn't work. Times row 0. And so we're going to go up here and look at rule number 1. Linear combinations do not change the determinant. See, up here, rule number 1. So we go back and see, so the scalar remains 1. We're going to keep it that way because the determinant has not changed. So now we're going to try to get rid of the G. We're going to do the same thing. We want to mutate row 2, so we click on row 2 first. Row 2. Now we're going to do the same thing. We're going to subtract G divided by A times row 0. And then once we're done, once we've got the expression that we'd like, we press evaluate or we press E. There we go. So R1 goes to R2 minus G over A times row 0. And it formats it in a fraction for us. So since we've used a linear combination, we have not changed the determinant. See, this remains 1. So now we want to reduce this guy. These expressions are very complicated, and we could just click on each one and multiply them out and stuff, but that would be so one thing we could do is we could click on row 2, which is the one we'd like to mutate. We can subtract this huge expression divided by this huge expression times R1, and then we get the answer. So let's click evaluate, and that creates a 0 here. So now that we've reduced the matrix into upper triangular form, all we have to do is multiply by the elements in the diagonal to compute the final determinant. So A times this big expression times this big expression, then we evaluate it, and we've now computed that the determinant of any arbitrary 3 by 3 matrix of the form A, B, C, D, E, F, G, H, I is equal to negative AFH plus BFG plus CDH minus CEG plus IAE minus IBD. Thank you very much for watching. Goodbye.